Hello and welcome back to the fourth part of Deltek's Physics 111 Exam 2 Preparation and Practice Exam covering forces and energy. In this particular video, we're going to talk about work, that is work energy, using the physicist's definition of work, meaning force times displacement. We'll talk about IMA, which is the ideal mechanical advantage. That tells you how well a machine helps you in terms of lowering the amount of force you need to apply. And then we'll talk about efficiency of machines that are not 100% efficient. And then finally, power, which is work energy per time. So in this problem, it says Amy carried a 50 kilogram mass up to a height of 18 meters in 25 seconds. And Bay carried a 15 kilogram mass up to a height of 60 meters in 40 seconds. Assume for this problem that G is 10 meters per second squared. And since this is a work problem, work is a form of energy, energy doesn't require a direction, it's a scalar. There can be positive and negatives to it, but those positive and negatives refer to the direction that work is done. In other words, person X does work on object Y, then we would use the signs. But for this, all energy forms are going to have positive values. Okay, so the part A says who did more work and why. In other words, we have to calculate how much work Amy and Bay each did. So let's start by writing down the formula for work. And the official formula for work would be work equals the force times the displacement or distance times the cosine of the angle between the direction of the force and the direction of the displacement. But we're not going to worry about that. These problems are all going to be problems that involve force and displacement being in the same direction. So we're going to keep it fairly simple. So work equals force times displacement or distance. And if you look at the problem, it says both of them carried a mass up to a certain height. So it's a vertical form of distance. And therefore, since they're lifting a mass up, they have to put a certain amount of force in, and that force must be equal to the weight that they're lifting up. So they're really concerned with the weight force times the distance, but the distance is vertical, so we would just call that distance height. And as you remember, the weight force, F sub g, is calculated as m times g, g being 10 meters per second squared here, and the masses are listed in the question, and then we multiply it by the heights listed in the question. So we have a formula for vertical work that's simply mass times g times height. So let's work out that value for each of them. So for Amy, it's a 50 kilogram mass times 10 meters per second squared for G, times the height she's lifting, which is 18 meters. And for Bay, she is lifting 15 kilograms of mass. Remember, kilograms are mass, not weight. So you have to multiply it by G, meters per second squared. And her height is considerably taller, 60 meters. And now you just pull out your calculator and you calculate, and you find that Amy's work is 9,000, and we know the unit for work, like all forms of energy, is joule. So it's 9,000 joules. Well, when you multiply 15 kilograms times 10 meters per second squared times 60 meters, you also get 6,000 joules. Now, the reason why these two are equal is not some magical property. It's I purposely made the numbers work out so the same amount of energy would be calculated for each person. One person had a greater mass but a lower height, and the other one had a lower mass but a greater height. And they both ended up performing 6,000 joules worth of work. So who was more powerful? Well, neither one. They both were exactly the same. And the y is answered by the math. Okay, now let's look at the next part of the problem. It says, who was more powerful? In other words, who used more power? Well, the formula for power is pretty simple as well. It's the work energy divided by the time. So if we want to figure out the power for Amy and the power for Bay, we just take each of their work energy, which was in both cases, was 9,000 joules, and we divide it by how many seconds each one used to do that task. So Amy took 25 seconds and Bay took 40 seconds. So we plug those numbers in, 25 seconds, and 40 seconds. And when you do the division for Amy, it works out to 360 joules per second. But joules per second is the same thing, the official unit of power, which are watts, which we abbreviate with a capital W. Bay's power works out to be 225 joules per second, or 225 watts. So the answer in this case is that Amy used more power, or you can say Amy was more powerful, to be kind of cute. And that's it for that kind of simple work and power problem. Let's look at the next problem. It says a particular machine is used to decrease the force that a person must use to move a heavy object from one location to another. So what machines do frequently is they don't change how much work you have to do. You can't change how much work energy a job requires, but they can change how that work is done. So we know that work is force times displacement or distance. Machines allow you to use less force, but you have to use more distance in response. So you don't get anything for free. You don't get energy for free, but you can play around with the relative amounts of force and distance or displacement, depending on how you want to view it. So a machine never gives you something for nothing. The work input that you put into the machine has to be at least as equal or maybe even greater if you don't have 100% efficient machines than the work output from the machine. That's if the machine is 100% efficient. If the machine is less than 100% efficient, you have to put even more work in. What the machine, though, does is allow you to use less force, but of course you have to pay the price of pushing that force a greater distance, maybe pushing it up a longer ramp or pulling more rope in a pulley, etc. So the trade-off here is that you can use less force, but you have to use a greater distance or greater displacement. So for a machine that has an ideal mechanical advantage of 10, what does that mean? It means you can use 1/10 of the force, but you have to either push the object or pull a rope 10 times more. So for example, if I'm using a ramp that has a 10-meter slope up the ramp, but it's only 1 meter high, that's a 10-to-1 advantage in the machine of the ramp. So I can use 1/10 of the force, but I have to push it a 10 times longer along the length of that long ramp. Or if I was using a pulley, if I wanted to lift something 1 meter and I had a mechanical advantage of 10, it means that even though I wanted to lift an object only 1 meter, I had to pull 10 meters of rope. So the trade-off is you can use 1/10 of the force, but you need to apply the force 10 times greater distance or displacement by 10 times more distance or displacement, whichever way you want to put it. Okay, so moving on to the next question. If your machine is not 100% efficient, so remember, all of the work we've talked about so far, we're assuming 100% efficiency. But if you have a machine that's not 100% efficient, now the work you put in to the machine is not the work you get out. You lose some of your effort. So only a certain percentage of the work you put in actually comes out of the machine. And this can happen because machines are not perfect. Machines have friction in them. Some of the energy that you put in might be lost to things like heat or sound or some of these other non-mechanical energy forms that we'll talk about later. Okay, so it says if your machine is not 100% efficient, you need to input extra work to generate the expected work output from the machine. That is, in theory, the work input should be equal to the work output, but the fact is, in reality, machines are rarely perfect. There are only a few kinds of machines that are 100% efficient. Heaters tend to be 100% efficient because all of the electrical energy you put into the machine can be turned into heat. It's easy to turn things into heat. Consequently, we usually find that when efficiency is not 100%, the work input we put in is greater than the work we get out. So, for example, suppose your machine is 74% efficient. How much work must you put into a machine to get a work output of 4,500 joules? Well, we have two different formulas you can use for this, but I think the easier version of this would be the formula that says percent efficiency, and I'm just going to abbreviate efficiency as EFF, times the work you put in, the input work, equals 100% times the work you get out, the work output. And another way to read this, you can, when you read equations and you want to turn them into everyday English, replace the word times with the word of. So we have, in this case, 74% of the work we put in, which we don't know, will become 100% of the work we get out. And the work we need to get out in this case is 4,500 joules. So we're just solving for the work input, how much we have to put in to get 4,500 joules. We would expect to have to put in more than 4,500 joules because the machine isn't perfect. We'll lose some of our input energy. Well, if you divide both sides by 74%, you'll see that the 74% on the left side of the equation just cancels out, and you're left with work input equals this fraction. So it's just a matter of taking out your calculator and multiplying it through. Well, 100 times 4,500 divided by 74 equals 6,081. Percents cancel percent, and all we're left with is joules. So our answer, of course, is in joules. This is the work input. Now ask yourself, does this make sense? If I put in a little over 6,000 joules and I get out 4,500 joules, is that what I'd expect if the machine was about 3/4 efficient? And 74% is roughly 75%, 3/4. And yes, that makes perfect sense. Okay, let's look at the next problem. So now we have a problem where we're actually using a tool and we're told the tool is 100% efficient. It's a ramp, which is technically called an inclined plane. It's basically a flat surface that's inclined to a certain angle. And this particular inclined plane, it says there's a block weighing 800 newtons being pushed up the inclined plane as shown in the diagram. And as you can see, the length of the inclined plane up the ramp, it's 20 meters. But the rise in the ramp, it gets to a height of 4 meters. So you basically have two choices. Not use the ramp and just lift this 800 Newton weight straight up 4 meters, or use the ramp and push it up this longer surface with less force. If you were to lift it straight up 4 meters, the force you have to lift it with is the weight of that block, and that block weighs 800 newtons. But you don't have to use the full 800 newtons if you're pushing along the length of a ramp. That's the beauty of a ramp. So the question here says, what is the ideal mechanical advantage? Well, there are two ways to calculate the ideal mechanical advantage. It is either the ratio of the two heights, the long height over the short height, I'm sorry, not height, the lengths, the distances. So you have the distance input, which is always going to be the longer one, over the distance output. That's what you get out of it. You get to lift it by 4 meters. And so 4 meters is what you get out of it, but in the trade-off, you have to push it a further distance. You get to use less force, but you have to push it 20 meters. Well, that's a ratio of 5. You'll notice the meters cancel with meters. And this ideal mechanical advantage of 5, it has no units. It's a unitless value because it's a ratio of two different distances. Now, remember, I also said it could be a ratio of two different forces. Not only is the IMA the ratio of the distance input, how much you need to push it, over the distance output, how much it ends up being lifted, but it's also a ratio of the force output over the force input. I've switched the input and the output for forces. Okay, so before we get to that second version of the formula, let's look at the next question. How much force is needed to lift the block without using the inclined plane? So if you just had to lift an 800 Newton block straight up 4 meters, well, you need to use a force that will balance the weight force. Well, the weight is 800 newtons, so that means the force output that you're putting into it, that is ultimately coming out, is also 800 newtons. And this would be your input if you didn't have a tool, but hopefully it's the output if you do have the tool. In this case, the tool is the plane. All right, so the next question says, all right, how much work is required to lift the block without the inclined plane? Well, you're told the inclined plane is 100% efficient. What that means is the work input, in other words, what you have to do, is exactly equal to the work output. So in theory, you could calculate either the work input or the work output for this answer. But the fact is, for the work input, we have no idea what force we'd have to push the block up the ramp. So we can't calculate the input one directly, but we can calculate the output one directly. And the output one is the force times the distance, but in this case, it's the force going straight up, so it's the force due to gravity, the weight of the object times its height. And what is that equal to? Well, we know the thing weighs 800 newtons, and we know we're pushing it up 4 meters, so that's 3,200 joules of work. Whether we lift it on our own without the ramp, that would be the work output, or we really do work input with the machine and let the machine do the output of raising it up to 4 meters. So we know the total energy is 3,200 joules. All right, so part D says, given the IMA you calculated in part A, which we knew is 5-fold, how much force would you need to use? Well, we know the actual weight of the object is 800 newtons. All we have to do is divide that by 5 to get the force that we really do have to put in when we're using the ramp. So 800 divided by 5 is a much smaller 160 newtons. Or you can just say the work input and the work output are the same and write the formulas for that. You can do the force in times the distance in, that's the work you're doing on the ramp, would be equal to the force out times the distance out. Well, that's lifting it straight up. So you could rewrite that formula. We don't know the force in, but we know when we multiply it by the longer distance, 20 meters, it will be the same result as if we lifted the 900 meters straight up, the 900 newtons straight up by 4 meters. And then we solve for this by just dividing both sides by 20 meters, and that gets rid of that term. And you come back to a formula that will calculate the same 160 newtons of force that you need to use when you're pushing it up the ramp. So you can do it either way. There are at least 2 different ways to solve this problem. All right, so how much work is required to push the block to the top of the incline? Well, it's a 100% efficient machine, so the work you have to put in when you're pushing it up is the same as the work you get out if you didn't use the ramp at all, and we already know that that is 3,200 joules. It's the same amount, and it's the same amount because the machine is 100% efficient. It uses all of your input work energy and turns it 100% into output energy. And we'll stop right here.